Good morning, ladies and gentlemen. I hope you enjoyed last night the gala dinner. At least to me, the house band or the party band was just something really extra, and the food was also really excellent. Everything that is good ends, so today is the last day of the conference, and we will now have, in this session, 2 keynotes. And I would like to remind you that this session is recorded, and it is available from all the social media platforms, and the link is also available at the website. So just to let you know, and without further ado, let us go to our first keynote speaker. He is Andrea Conti. Andrea is a professor at the University of Ferrara and a research affiliate at the MIT Wireless Information and Network Sciences Laboratory. His research interests involve theory and experimentation of wireless systems and networks, including network localization, distributed sensing, and quantum communication. He received the H.T. Puskas Tivadar Medal and the IEEE Communication Society's Stephen O. Rice Prize in the field of communication theory, and the IEEE Communication Society's Fred W. Ellersig Prize. Dr. Conti has served as an editor for numerous IEEE journals, as well as chaired numerous conferences. He has been elected chair of the IEEE Communication Society's Radio Communication Technical Committee, and he is co-founder and elected secretary of the IEEE Quantum Communication and Information Technology Emerging Technical Subcommittee. Professor Conti is an elected fellow of the IEEE and of the IET, and he has been selected as an IEEE distinguished lecturer. So, Professor Conti, please, the floor is yours.
Hello, good morning, everyone. Thank you, Art, for your kind introduction. Thank you, Luis, for your kind invitation, and all the organizing committee for having me, and also for organizing this great conference. It's really a pleasure for me to be here and share with you something I have learned over a number of years, and that together with some new results in the field of localization. And in particular, I will put this talk in the framework of 5G and beyond towards 6G localization and localization of things. And this is really something I have learned over the years thanks to the work with students and the discussion with many collaborators at MIT WINS Lab, at KNIT, YLab, and many other companies and research centers in Europe and outside Europe with which I've been fortunate to collaborate with in the framework of European and non-European projects. So it's really a pleasure for me to be here and share you a few aspects on localization. And this is the outline of my talk. I would like to start with some preliminaries just to motivate a little bit about the importance of localization nowadays. Even if you move into the booth of this conference, you see already so many demonstrations that utilize position and information that this shouldn't be really needed as a motivation. But I think that I will start from that for having some ground truth. And then I will talk about what 3GPP asks us for localization. And I will touch upon a little bit of foundation that is needed to develop algorithms. And then I will show you a few results in beyond 5G settings, regulated beyond 5G settings. And then I will show you I will move into device-free localization and show you some video with some experimental activity ongoing. So let's start with some preliminary. Location awareness is becoming more and more important. In one sense because it enables a myriad of new applications. Just to mention a few, factory of the futures that many companies are really interested into, and we have also heard in previous keynotes the importance of it, as well as agriculture of precision, drone delivery and safety, autonomous vehicles and automated guided vehicles inside factories, the tracking, the counting, and the monitoring of flow of people, so not only information about the position of each person, but also some analytics or location-based analytics related to the position of the people, but also for augmented reality or virtual reality, for example, in digital humanities. And in general, every time we want to perform some distributed inference task where we have distributed sensors that can be really heterogeneous, provide us a heterogeneous measurement, and we want to estimate or determine or reconstruct a spatiotemporal field based on noisy measurements from this sensor. And as we know since the Shannon theorem in the first years of college, the measurement makes sense, or you can really utilize them in a proper way only if you know from the time in which they were taken, but also from the position in which they were taken. So multidimensional sampling is important. And many other location-based analytics. So we are really in the era of Internet of Things. So we call localization of things the process of locating, tracking, and navigating any possible nodes. That could be a person, could be a vehicle, can be any object. And this node can be collaborative or non-collaborative to the localization process. So during this talk, I will touch upon active and passive localization in this sense. So considering the motto of this conference, one of the questions is how can localization of things and location-based analytics can enable a better, safer, sustainable society? And I think the answer is that localization now and position information play a key role in a number of tasks, like for building digital twin or digital cousin of an environment or of a network, for orchestrating the network resources, for assisting fragile people. And we will see some experimental examples on that, on device-free localization, for recognizing action of people, how they move, how they behave, by preserving their privacy, because this is all based on, will be all based on reflected radio signals. For network control, which is becoming more and more important in our factories with cyber-physical systems that we want to control. For tactical networks, when we want to design our network and orchestrate the network so that it can really provide us all the resources that we need for a given task. And also for predicting health disease. I have some colleagues in in cognitive sciences that ask me, can you, with radars, predict how people change the way they are moving or they are walking, and can this be used via artificial intelligence to predict diseases in the brain, for example? And in order to understand the localization of things, our view is that you first need to know a little bit of theoretical foundation. And the theoretical foundation is really the key to understand how, what are the key parameters, the important aspects to know to design a location-aware networks. And then once you know the foundation, you know better how to exploit the technology and all the type of measurement that technology can provide us. So we will talk about inter-node measurements, so measurement exchange among the nodes in the network, or intra-node measurement when you have initial measurement. How to exploit prior information given by knowledge of the environment on the mobility model, as well as the deployment of your networks in a certain environment. And then you need to develop algorithm based on the foundations, and this algorithm will be application of statistical inference, and will take into account mobility and measurement models, will take into account cooperation among nodes in both space and time, as well as nowadays we talk more and more about the fusion of heterogeneous measurements, so data fusion is another important aspect for our algorithm. And then these algorithms provide you with positional information that can serve for application of the different kind, like those that I mentioned earlier. And this is a cycle that we all know as an engineer and developer is really a cycle built upon theoretical foundation. And in the context of cellular networks and 5G and beyond, 3GPP, that is providing us specifications for the cellular networks, is putting put together some service level requirements, some KPIs. And these KPIs are quite challenging, as this table shows. So first of all, what the KPI are. So you have 7 positioning service level in terms of absolute or relative positions. And one KPI is the accuracy, is the localization error. And for some of these KPI, you can see that the requirement is really below a meter, a few tenths of centimeters. And the accuracy is in a horizontal plane, but also vertical, thinking of 3D networks, aerial networks. And they also, another key performance indicator is the availability. So what is the fraction of time for which you need to reach that performance? And what is the latency? And you see that some of these scenarios, which could be indoor, outdoor, with people or objects that move also fast, is quite challenging. And because it is quite challenging, you really need to fuse data from heterogeneous measurements and from all the type of technologies that you have in a certain environment. That's why we talk about data fusion of measurements that are radio access technology dependent, so built in the 5G new radio, for example, or radio access technology independent that are provided by other technology in the ecosystem. By the way, since release 16, really, the 3GPP specification talk about ecosystem, so it is already in the view that you need to fuse all these measurements. And the verticals are also defined in different types of settings and environment, for which you will need the public or private or dedicated networks. And this is really also an opportunity to develop a new location-based analytics of individual and groups. And I would like to mention also that location awareness is a win-win situation, because if from one side you have all these new technologies and measurement made available by 5G new radio. For example, you have dedicated signal, you have the capability, especially in FR2 at millimeter wave, to do perform measurements of angle of departure. You also have the heterogeneity provided by other technologies like 5G RAT independent technology, and all of these are resources that can be dedicated to localize your object or people or vehicles. But on the other hand, once you have a good information about the positional state, you can also use it for improving the network management. So the knowledge of the position of your nodes really help you in a better management of your network resources. For example, we here in the previous keynotes talk about, Ted Rappaport was talking about beamforming and beam tracking. So in order to, especially at higher moving up to higher frequency, you can have multiple antennas, so you can do really a small beam width, and you want to focus your beam toward the object so that you don't interfere in the other areas. And you increase your SINR, and therefore you increase your throughput in communications. But if the object or the node is moving, you also want to track with your beam that object. So localization is becoming more and more important also for the network and at both radio and core, because you can also do better network orchestration. So a little bit of foundation. So we have nodes that move in the environment. At a different time, they are in different position, moving along trajectories. And these nodes exchange measurements, and measurement can be with other nodes, so there are inter-node measurement. They can be through cameras, through radio signals. They can be through LIDARs, optics, many types of measurement you can have available, as well as you can have inertial measurement unit, accelerometer or barometer or other type of unit inside your node. And you want to fuse together all these measurements to estimate the positional state of the node. And what is the positional state of the node? Well, all of us maybe is thinking now about the coordinate of the node, but there can be much more. There can be the acceleration, the velocity, the angular velocity, the orientation of your node. And you really want to estimate this parameter. And so there are a few works on this theoretical foundation that, based on Fisher information analysis, tell us that any estimator of your positional states has a mean square error, which is lower bounded by something that can be extracted from a Fisher information matrix. And authors of this work has also determined an equivalent form of this matrix that is of smaller dimension, but contain all the information associated to a specific agent. And from there, by taking the trace of the inverse of a small dimensional matrix, 2 by 2 or 3 by 3, depending on if you are 2D or 3D localization, then you can obtain your square position error bound, which is the best that you can do with any positional estimator. And why this is needed? Well, this could be needed to have a benchmark to know the gap to be filled with your technologies. But it also depends for certain SNR region how tight your bound is. But more than that, this drives the development of the algorithm because it tells you which parameters really matter. And in fact, something that the equivalent Fisher information matrix instruct is on the direction in which you gain positional information when you exchange measurement with a certain node. Also, the intensity of such information. So, for example, if we take a measurement with a certain base station or anchor with this agent, we know that we gain position information along that direction. And there is also a geometric interpretation in terms of information ellipses that is given in those papers. And the bigger the ellipse is, the more positional information you gain from that measurement. So you want to make this ellipse bigger and bigger. And the way you make this information bigger and bigger is also by improving the SNR or improving the squared effective bandwidth. And the effective bandwidth is the Gabor bandwidth, meaning that it's not just the bandwidth, it's the Gabor bandwidth. So if you have a 20 megahertz signal by doing, for example, your LTE carrier aggregation at 900 megahertz, or if you have your 20 megahertz around 2 gigahertz, or if you use your 20 megahertz around 30 gigahertz, the higher you move into the frequency, the more positional information you get with that measurement. Okay, and of course there is then a trade-off with the SNR and the coverage at higher frequencies. And another advantage of this foundation is that it tells you also how you can improve your position information based on the position of your cooperative agents. So if you do cooperation in space and time, therefore, if you are, for example, in a factory and you want to decide with which other robot you are cooperating with, and you have a plethora of robots you can exchange measurements, you have a tool to determine with which robot is better to exchange measurements. Because, for example, if I use this as an assisting node, I gain information along this direction, so my information ellipses would increase in this way. And if I also do cooperation with this other node, I will gain even more along that direction. So you really want not to align the measurement along the same direction. You want to spread your measurement in the area, and these tools tell you how to do it. Once you know the foundation, you can develop algorithm. And there is a vast literature of algorithm on localization. Sorry. Yeah, okay. There is a vast literature of algorithm in localization, and we all know about trilateration or multilateration. When you have distance measurements, you know that if you estimate a certain distance, you know that you are over a circle around the node with which you exchange the measurement, and then you add another measurement, and then you intersect the two circles, and then a third one if you are in two-dimensional plane, and you should solve the ambiguity. But this only works in the ideal world, because your measurements are really affected by uncertainty. And if you move into millimeter wave domain, in addition to the range measurement, you can also add angle measurement, angle of departure measurement, for example, because you have multiple antennas. So with antenna array, you can estimate the direction of your signal. But if you take our decision, what we call single value estimate, from each measurement, I measure with you, and I estimate directly what is the distance among us, and then among other pairs, appears, and I estimate this distance or angle of arrival. This measurement will be affected by the uncertainty, because if we are often in a wireless environment that are complex, look, for example, at this room with all the multi-path reflections, or in industries where there are, in factories where there are metal barriers, no line of sight, signal blockages. So all these uncertainty would really affect the performance of your algorithm. So we soon realized that we need to move from single value estimate algorithm to probability-based algorithm. And the probabilistic approach that we call soft information-based approach, in which we probabilistically account for all the possible measurements, all the possible value of the positional related metrics associated to a given measurement. And you can learn these distributions through some machine learning tool. And in fact, the way we do, for example, this is a picture that depicts what you can do in a cellular network setting. You have an offline stage where you have a training, some measurement with your base station. Then you can project your measurement positional features plane into a reduced dimensional plane. And you can then learn your generative models, and then you apply all this generative model every time a new measurement comes in an online stage. So what does all of this mean in terms of 3GPP type of measurements? So we consider a setting where we have base station, GNBs, in known position, where we have user equipments in unknown position, and the type of measurement that are available, at least according to 3GPP specification, I will be at the very end in the conclusion a little bit provocative on this type of signals, are reference signals, which are FDM signals already in the specification since some release ago. And with the positioning reference signal, you can do downlink time difference of arrival, for example. With the sounding reference signal, you can do uplink time difference of arrival. And by the way, the sounding reference signal is what is used also for channel estimation. And then through those signals and through some correlation, you can extract the time of arrival, the round-trip time, or the time difference of arrival. All these measurements you can extract both in FR1 and FR2. FR1 means sub 7 gigahertz. FR2 means at millimeter wave, around 30 gigahertz, depending on the countries where you are. If you move into FR2, you have MIMO, or massive MIMO, and you can also determine the angle of departure based on the received power from different directions. So let me show you a little bit of performance in 3GPP settings. And in order to do that in a framework of a recently ended European project, Locus, and in synergy with some other project in US, we have developed a localization simulator which is fully compliant with 3GPP. In terms of scenarios, deployment of the base station, parameters such as the antenna transmitted power, noise figure, all of that is well specified in the specification of 3GPP. And from there, you can determine the evolution of your soft information, which I will show you with a little video. So you see here a scenario which is according to 3GPP. And by the way, why 3GPP? The 3GPP scenario can never be equal to any scenario, real scenario that you have in mind. But there is the need for a ground truth. That's why companies specified some settings in which you can really compare different type of solutions. So here you see the deployment. This is an indoor open office deployment. These are base stations. Here you are doing angle of departure at 30 gigahertz with a reference signal bandwidth of 100 megahertz. This is how your soft information looks like and evolve in time. And while the agents are moving, you can also determine the empirical CDF of the localization error. And by the way, this is the empirical CDF, so you want to be to the left to the better. And you can compare soft information approach in blue with existing and current approaches in red and see what is the advantages in different bandwidth, in different settings of one configuration or the other. Okay, so we use this to determine some results and to have a better understanding on the evolution of the soft information in space and the time. So now, to be a little bit more concrete, we can look into some recent results that we had according to 3GPP specification. This is urban micro and indoor open office scenario. This is how these two settings are defined by 3GPP in terms of base station, location, and all of that. And this is these two pictures represent the average number. To the left represent the average number of position that will be in line of sight with no base station, or line of sight with at least one base station, or line of sight with at least two base stations, etc. And here you can see the empirical CDF of the horizontal localization error. With these dots are the results that are in technical reports by 3GPP, so that some company publishing this technical report. And the curves are what, with the same measurement, you can obtain by using a probabilistic approach. And you can see that you move to the left, so it is really better. And type 1, type 2 means two different frequencies in FR1 and two different bandwidth for your reference signals. It is also of interest to understand what will be, if any, the gain of moving 2 millimeter wave. So we have a few results here where we have in indoor open office at FR1 and FR2. So again, FR1 means below 7 gigahertz. FR2 means at millimeter wave, around 30 gigahertz. You can see your CDF for the horizontal error. The dashed dotted lines represent the performance when you apply some classical weighted least square algorithm that by reverse engineering seems to be the algorithm that we're taking into account in those technical reports. And the continuous line are the results with the soft information, so with the probabilistic approach. And you can see different type of measurement, downlink TDOA through the position and reference signal, uplink TDOA through the SRS, multi-cell round trip time. And you can see how in FR1, in the left figure, and in FR2, at millimeter wave, in the right figure, you can improve your performance through some probabilistic approach. And really the key here is that probabilistic approach enables you to account for a variety of wireless conditions in your environment. That's why they play a big role here. And also, if you recall what 3GPP specification asks you, 99% errors below a meter, this is something that seems, at least in 3GPP setting, you can obtain. We also look into data fusion. So how can we fuse measurement from 5G new radio and from Wi-Fi? And in a certain environment, again, 3GPP indoor open office, here you see your base station that are this LED circle. You see the Wi-Fi access point that are the blue triangle. And here you have the ECDF of the horizontal localization error for single value estimate using solo technology, Wi-Fi only in red, dash red, and 5G only. What you gain by applying a probabilistic approach, and what you gain, again, when you fuse the data and the measurement from Wi-Fi and 5G. So this is, if any motivation would be needed, this is, again, another motivation for data fusion and for heterogeneous localization. Really exploit all the wireless resources that you have in a certain environment. Then we also look into the industrial factory environment defined by 3GPP. Turns out to be of interest for many companies that look into the factory of the future. And in particular, 3GPP has defined a number of indoor factory environments. So what I'm showing you here is some results related to the most challenging environment, which is called DH, which has much higher probability of no line of sight. And here you see a picture that tells you with the 18 GNBs in certain area. Now the GNB, you shouldn't think of big tower. GNB are really of the dimension of a Wi-Fi access point. You can see what is the line of sight conditions in such an environment. And we also try to understand if we can obtain similar performances with much less infrastructure, only 12 instead of 18, with respect to those specified by 3GPP. We noticed that this really called for no-line-of-sight identification method. We developed some no-line-of-sight identification methods that evolve with respect to classical ones that are binary, just aim to determine if you are in line of sight or no line of sight, providing a probabilistic description of your wireless environment. This can be done by assembling a group of weak learners and learn the environment based on some feature in time and amplitude that you can extract from the received waveform. And then we tested some algorithm on this environment, and we have seen with a larger number of GNBs or smaller number of GNBs, number of GNBs means more no line of sight conditions. And so you can see that the improvement from SVE to SI is significant, but is also even more significant if you use these no line of sight identification methods. And we did this both in FR1 and in FR2, okay, with different type of measurement. And again, the real message is that the probabilistic approach help even in no line of sight identification, okay, rather than being binary, try to have a distribution or a description of your environment which is richer. So in a few minutes, I just would like to move into device-free localization of things, because so far we are considering in a 3GPP settings localization where your agents really want to exchange measurement because they want to know where they are. But what about if you want to localize vehicles or people that are not equipped with any devices that is connected to your network? This is the so-called device-free localization. And localization can really be active or passive from both the perspective of the source and the target. In fact, in the case of active target, which is the case we consider so far, we have the user equipment as our target. In the case of passive target, we are calling it device-free localization. But also in terms of the source, your localization process can be active or passive. So if you have an active source, you have a signal which is dedicated to localization. If you have a passive source, you are exploiting signals that are in the environment for other purposes, for example, communication, so that you use as a signal of opportunity. So we really are in the device-free localization in the framework of sensor radar networks, so networks of radar that could be monostatic or multistatics, and these open up to joint sensing and communication, or as someone call it also joint radar and communication, which is more and more important for autonomous vehicles. And the difficulties here is that you are only relying on reflected waveforms. So while I'm moving, I'm reflecting electromagnetic waves, and receivers perceive a waveform that vary in time, and there are micro variation of the received waveform that depends on where I am and how I move. So you need to infer from this small variation with respect to the amplitude of the signal, you need to infer where the target is. And this is challenging and requires some effort in terms of clutter removal, in terms of filtering, in terms of probabilistic data association, because if you have multiple targets in an environment, and they might also cross the path to each other, and you don't want to lose them. And remember, you are only relying on the reflected waveform. And so we developed some algorithm based on that touch upon all these aspects, and we tested it in a real indoor environment. So here I'm showing you a little bit of experimentation. This is an off-the-shelf radar, which is a MIMO radar, operating at millimeter wave, 77 gigahertz. And here you will see the real environment, where in a moment a few people will come in. Here you see the map of the environment. So these squares represent the squares that are in the real environment, just to give you a perception of the accuracy. And here you will see the range Doppler map from the radar. So we see now that after a few seconds of learning of the environment for clutter removal, there is a person that moves in, there is another person that moves in, and from the received waveform, you can extract this information on the coordinates and the velocity, and you can do this in multiple targets. Okay, and so we are testing this in indoor environment. And one of the difficulties is that, of course, the reflection of the received waveform from one target can also bounce on another target. So how really to extract all this information is a part of the challenge and of the excitement of the problem. We also move forward and say, in addition to multi-target tracking, can we also identify the tracking? Can we recognize if the target is, for example, a person or a robot, which is practical importance for the factory of the future? So here you see another short video where you will see person. You will also see a little robot that will be moving. So you see the person enter, based on the way he moves, is first evaluated and then recognized as identified as a human. Then there is a little robot that enter here, very little robot, and this is recognized as a machine. And by the way, this algorithm have no prior information at all about possible directions of your robot. This black line is only needed so that the robot can follow a certain path, which is not known by the algorithm. And so you see the accuracy on one side and also the type of identification that can be done. Okay, I think I am almost to the end, but I hope you understand that this is this can be helpful, this particular device field localization, not only in factories but also for assisting fragile people. In fact, one of the things that we are working on now is also to recognize actions. Okay, not only track multiple targets, not only identify them, but also recognize how they move. For example, if they fall down, or if they move arms in a certain way. And this is important for safety, but also for assisting fragile people, because I think, all know that most of the damages for fall down, especially for fragile people, are caused in the bathroom, and you don't want to really put cameras in your bathroom, or people don't want to put camera in the bathroom. So a radio solution that preserves the privacy because it's only based on the reflection of the waveforms could be a key. Okay, I'm gonna, we also used fixed wireless access from 5G in a parking lot to estimate angle of departure and determine the position of cars. So what is next, moving towards 6G? And I'm going into the conclusion. So for sure, I think that we will see more and more joint sensing and communication, as well as the simultaneous localization and mapping. This is already a reality that is happening, and people will work more and more. Not only in bidimensional plane, but also in 3D. Security and integrity is very important. Also, intelligent surfaces, how to shape your electromagnetic environment in order to do a better communication, but also localization, and how to exploit quantum mechanical properties, quantum illumination, quantum radar for better sensing. So we have started doing a few works in this aspect. I think probably the slide or the video will be available soon. So if you are interested, you can look at, or we can talk a little bit more offline. How to shape your radio propagation environment using intelligent surface with the purpose not only of communication, but also localization to reach better your anchors or your base station is something we have looked into. And also how to design the quantum states in order to communicate or have better sensing is something we are quite interested and we are looking into that. So as a conclusion, I hope I send you a message that localization of things is essential for various emerging applications. Probabilistic approach, such as the soft information approach, provide richer information than single value estimate. In particular, when the wireless environment is complex, these probabilistic approach are really helping you in having the accuracy that are close to the service level requirement that were fused by 3GPP. And if you allow me to be a little provocative, I should be showing you results according to 3GPP specification that really give us excellent type of signals to do localization, like positioning reference signals. But at least in Italy so far, maybe also in other countries, if you talk to operators or manufacturers and you ask them to use their GNBs with these signals, they tell you, oh, we might have it, but we don't really open up yet, because these are not for the mainstream of services for communication. So I hope this type of result convince you that this is really the way to go, and that soon it will be the opportunity to really do experimentation based on these type of signals, not only PRS, but also side links for communication among agents. And in case you are interested and you want to start in this exciting field of localization, I know that recently Communication Society by IEEE has put together a series of best readings on these topics, and this is the link for you to look. So as a takeaway, space is the next frontier. We want to explore space in many dimensions. And this is not a sentence only from Star Trek movie, but this was a sentence by Bill Lindsay, the father of digital synchronization. If you want to explore the space, you need to know where you are, so location, location, location. And with this, thank you very much.
Thank you, Andrea. That was a fascinating talk. We have still some time for questions. Are there any questions in the audience? There is one. There is a microphone over there.
Now I see you all.
Hello, I'm Konstantinos Dodin from the University of Luxembourg. Thank you very much for the very interesting presentation. I would like to ask you actually to stay a bit more on your take regarding intelligent surface for localization, because I mean, since in 6G and beyond networks, we require very accurate localization, sub-meter or even centimeter level localization in various applications such as autonomous driving, IoT localization in factories. So inevitably, we need to go to high bandwidth signals such as millimeter wave bands. But on the other hand, actually, these carriers are highly susceptible to blockages. So one direct, straightforward solution is to heavily densify the network with active anchor nodes. But it's not viable, at least in my perception, in terms of cost and energy efficiency. So to reach to that high level of accuracy, would you say that maybe intelligent surface is the only viable way, or we can still actually play it around with active nodes and being, let's say, cost and energy efficient, let's say, counteracting the problem?
Okay,
thank you.
Thank you for your question. First of all, I totally agree. Sustainability is important. It's part of the motto of the conference, and therefore we cannot just densify and densify and densify the network unless we really have a full knowledge of the energy consumption, and we look into the overall energy consumption. So this is an important problem. In complex wireless environment, there is still space to develop some signal processing techniques that help you without the need of super densify your network. I hope a few results that I've shown in compelling, challenging industrial factory scenarios have shown that with no line of sight identification. But definitely you want to shape your wireless, your radio propagation environment, and intelligent surfaces are a way to go. And a few works that we have done looked into how to move from discrete intelligent surfaces into a continuum to have a better beamforming through that, and how to exploit the beamforming with the purpose of localization and not only communication, and also moving into higher frequency, how to have a wideband. We provided a wideband model for intelligent surfaces rather than a narrow band model that were available earlier. So yeah, thank you for the question. I think there is still space for signal processing, but intelligent surfaces is something that is going to happen in the next generation. Thank you.
Thank you very much.
Yes, thank you. Thank you very much. As a token of our appreciation, we have always a small gift for our keynote speakers.
Thank you.
So here you go, and
I appreciate it.
thank you very much once more, and give a big hand for Andrea.
Thank you. It's a pleasure to be with you all. Thank you again for the invitation.